Okay, I'm gonna share the screen. So, and then do kind of a general, probably like a, I don't know, 3 to 5 minute intro or something like that. So just, you know, bear with that. Okay, 1 second here.
And I'll probably turn off my video for the recording, right. To be honest.
No, that's fair enough. Hold on 1 second. Okay. Let's start in a second here. Too many windows open. Okay. All right, sharing the screen now. Hoping that works.
Yep, I can see it.
Okay. All right, so you can see the screen share, okay?
Yes.
All right, so we're gonna get started here. Quick intro, talking about work rate and distance rate problems. These tend to be, you know, they could show up anywhere on both the GRE and the GMAT, but they tend to be a little bit more, you know, a little bit more complicated. You know, so you could find them in more difficult question categories. Reason is that they are often very text heavy. So what you want to do when you're dealing with rates, first of all, kind of think about kind of how they're going to. I got a newcomer. Hi, Rashika. Just got started about a minute ago. All right, and you guys are both welcome to you know, either use the microphone or the chat window here, and I'll respond as best I can. So we're talking about rates on the GRE and GMAT, and what makes them difficult is there are usually kind of, you know, they're very core concepts, but they're not always easy to spot. All right. So essentially what you're looking at, the core idea between any kind of rate question is the work, right? Time, well, let's see, let's start with here. Rate times time equals your total, whatever, equals your total. All right. So if you're dealing with a project, a work project, whatever else, your rate times time is going to equal the, you know, the total project, the total work. All right. Or if you're dealing with vehicles or, you know, people moving around, whatever, rate time distance, rate times time equals distance. All right. This is very simple in terms of kind of the, you know, the basic quantity, right? You know, the basic equation is simply rate times time equals, you know, the total, whatever you happen to be talking about. The problem is these are, let's see. All right, Kathleen, you can still hear me, right?
Yes, I can.
All right.
I'll message and say that I can hear you.
Yeah, okay. Okay, so the idea then, all right, so when you're, you know, you've got the basic formula, what you want to do is you want to do whatever you can to make the problem as simple as possible. So if you've got a word problem, for example, and most of these are going to be word problems, all right, what you want to be able to do is basically quickly isolate all of the quantities. So let's actually take let's take a look at the 3 different types. So there's basically going to be 3 kinds of rate problems. Hmm. Okay. All right. So you basically got three types of these. The first type is a work rate problem where you have different rates. All right, so this is the kind of thing where it's going to be, you know, say you've got, oh, I don't know, 5 people. Oh no, let's say, I don't know, say John can mow 3 lawns in 4 days, and say Julie can mow, I don't know, like 4 lawns in 5 days. All right, something like this. These rates are going to be different. So what you want to do for these kinds of problems is do the best you can to standardize the rates, all right? So these are much easier to work with if you can figure out what is going on per unit of time. All right, so if you've got something like this, if John can mow 3 lawns in 4 days, so John's rate would be 3/4 of the lawn in 1 day, right? And similarly, Julie's rate would be 4/5 of a lawn in 1 day, right? So because we've standardized, once we standardize everything, we can actually kind of combine them, all right? So now we can say, well, okay, now we know the total combined work in 1 day, which is simply going to be 3/4 plus 4/5, all right? Whatever that happens to be, right? So, you know, multiply by 5/5, multiply by 4/4, right? So you end up with 15/20 plus 16/20 plus 16/20, and you end up with what, 31/20. All right, so working together, and a lot of these things, these kinds of rate problems deal with, you know, whether you're dealing with a combined rate or whether you're dealing with an individual rate, right? So you need to figure out which is which. All right, so the combined rate would be 31 out of 20 lawns per day, right? And then you want to keep in mind that rates are dealing with reciprocal relationships. Rate and time are reciprocal relationships, right? So if I can mow, if I'm doing a 31, 31 lawns in 20, or say if I'm doing 31/20ths of a lawn per day, you can also read that as 31 lawns in 20 days, right? Or 20 days to do 31 lawns. So what you want to be able to do is practice reading backwards and forwards, you know, to kind of practice reading the problems to figure out whether you're actually solving for a rate or time or whatever else, right? All right, why don't we move on to a couple of actual problems. Again, apologies, Kathleen. I know we've worked on these before, but you know, it's the same concept are going to apply. So let's move on to this one. All right. So still dealing with type 1, where the rates are going to be different. All right, how do you do those? Okay. So I know Kathleen has taken a look at this problem already. Okay, so let's see here.
Will you zoom a little bit more, Steve?
Pardon me?
Will you zoom a little bit more?
Zoom in a little more? Sure.
Yeah.
1 second.
Perfect. Thank you.
Okay.
That's better. Yeah.
Let's type to Rashika here. So let's see. Okay, so when you're taking a look at a problem like this, what you want to do is identify the key concepts quickly. All right. Okay, now granted, the GRE and the GMAT whiteboard are a little bit different. The GMAT's a bit more restricted. You know, GRE, you might be able to have some scratch paper to jot things down, but you still want to at least, you know, even if you can't annotate directly, at least be aware. We'll see, you know, so what do we need? We've got, you know, we've got 4 hours, right? Okay. Pump X is doing half of this. Okay, so if Pump X can do half the water, H2O, in 4 hours. Okay, that's one bit of information. Okay, so this is all X, right? Okay, then at some point we start Y. So we have X and Y working together, right? For that next part there. Okay, now the thing is, to figure out what's going on with combined rates, you want to figure out what's, you know, what each one is doing independently, if you can, right? So let's jot that down. All right, so figure, if it's not given to you directly. All right, now Kathleen, I know that we you know, we talked through a little bit. I don't know how well you actually remember this problem. Do you want to kind of you know, try talking it through?
Yeah, sure.
Okay.
So to first figure out the pump X rate, you want to sort of figure out like the standardized rate. So half of the basement in 4 hours would be the full basement in 8 hours. So that would be 1/8.
Okay, so I'll stop you there for 1 second. So exactly
Okay.
what you're saying here, right? So half the basement in 4 hours means a full basement in 8 hours. That gives you a standard rate, right? So our X rate is 1/8. Okay, so the rate, just put that here, equals 1/8. Okay, so now we've got rate X. All right, what's the next step?
So then you know that the rate X plus Y is 1/6 because the two pumps together can pump out the other half in 3 hours.
Right. So let's see. So slowing that down here, let's you know, flag that again. If you're doing the GMAT, you can actually like write this down here. But so half the water in 3 hours is going to be so the entire thing in 6 hours, right? So combined rate, as you're saying, X plus Y is going to be 1/6. Okay. So then let's say 1xy, so our combined rate is 1/6. That's what's going on here. Okay, now keep in mind, you want to be very careful to make sure that you're answering the correct question, right? So they're looking for how many hours? They're looking for the time. They're looking for pump Y. So you want to make sure, that you are not solving for rate, for example, right? So let's jot that down here. So we push carefully. Okay, so Kathleen, then what are we going to do with our 1/8 and our 1/6?
Yeah, so since you want to solve for the hours for pump Y, you would do 1/6 is equal to 1/8 plus 1/x. I'm glad this is coming easily. That means that it's stuck.
Yeah. Also, there's a couple ways of thinking about this too. It's like, you could do this as 1 over x, or you could do this as just, as just x, right? You just need to make sure that you know whether you're actually solving for the rate or the time. You see what I mean?
Right. Yeah, I would be solving for that x, but
Yep.
yeah.
Yeah. So yeah. All right. So what's your x then?
The x is 24 hours.
Yeah, exactly. So it's going to be 1 over 6 equals 1 over 8 plus 1 over, sorry, it should be 1/6 minus 1/8 equals 1 over x. X equals 24. All right, now what you did was a good move. You solved for time directly. So you're like, okay, the hours that we're going to need is going to be x. All right. Sometimes what I'll do, I'll just think about the entire thing in terms of rate and say, well, okay, this is one rate, this is the other rate. So then, I'd end up with 1 over 24, right? But that would be solving for rate, which is simply the inverse of time. So it doesn't matter which one you do, whichever one is more convenient. All right. So nice job. Okay, and that is basically the way in which you're going to solve problems where the rates are different. Then you also want to be aware of kind of how they might make things more difficult, all right? So, for example, be aware of the difference between, say, a 550, on the GMAT, or let's say maybe a 155 level rate problem, and a 680, right, or like say 167 on the GMAT. All right. So what might they do to make it harder? So they might ask more variables, right? They might they might have different starting and stopping points. They may combine it with other types of problems, like geometry, for example. Like maybe they'll have you on a conveyor belt or something like that. So there's different ways of making it harder, but essentially these are kind of the the core methods to solving these things. Let's take a look at the next kind. And again, apologies, Kathleen, because you've seen these before, but let's see how you.
Okay.
Okay, let's move up to the top here. Sorry for moving the screen all around. Second. Looks like we lost our other student, but that's okay because she will have hopefully the recorded version. Okay, so second kind of problem, and before we talk about that problem, let's actually go back to the this bit right here, to the second type of problem, which is where instead of having the rates being different, the rates are going to be the same. What do these kinds of problems look like? This is going to be the kind where you've got, say, X people can do Y things in Z hours, right? So I don't know, like say 14 people, 14 printers can print, I don't know, 350 sheets in 6 hours or something like that. All right, they're going to look like this. These are the kinds of questions where the rates are the same. They're still your standard rate time work problems, but you don't need to worry about standardizing the rates per unit time because it's already done for you, right? Because we already know, what each one can do. It's the same for everyone. So what you need to do for these is figure out how big the project actually is. All right, so instead of standardizing for time, standardize per project. on these. All right. So, for example, our first example, if X people can do Y things in Z hours, well, okay, so the total project is simply going to be X times Z. You can think about it in terms of like, person hours or machine hours, right? Or the time it takes for one individual to do the entire thing. All right. Okay, now, because the entire thing is, we're talking about Y things here, right? So the entire project is Y, Y amounts of whatever, whatever we're talking about. So in our case here, to figure out how long it would take to do one of those projects, you divide by Y. That makes sense?
Yep.
Okay, so XZ for the total work, right? Or XZ divided by Y for an individual project or event. Okay, so let's go and take a look at the next next problem here. All right. Okay, so okay, how do you know when you're taking a look at one of these problems whether you're actually dealing with a differing or the same rate? Well, here it tells you right there, same constant rate, right? Okay, so essentially what you want to figure out is what is going on in terms of the entire project. All right, so you want to talk me through this one again?
Yeah, sure. So the 4 machines operating simultaneously take 27 hours. So you would do 4 times 27 to get your full, or to get your one machine rate.
Right. So, and then if we're using our, so what do we have here? Yeah, so essentially what's going on, we've got 4 machines, right? The reason that this works is because what we're really saying, when it says 4 machines take 27 hours, what we're really saying is 27 hours per machine, right?
Right.
That's really what this is getting at, even though it doesn't say it flat out. And what's that equal?
That is 108.
108. Okay. Now, I remember when we talked a couple weeks ago, I know that you like using tables, and tables can be useful here. So why don't we actually kind of, just kind of map that out for the class here. So essentially what's going on, you're talking about is the number of individuals, in this case machines, right, times time per individual, time for each. Let's say time for each. And that's going to give us our total project time, total work, or total work hours, right? So we've got 4 things, we've got 27 for each one, our total is 108. So what you can do, because we're keeping this whole thing standard, right, you can scale up or down. So it's like, if you've got 6 machines, well, they can figure out, how to adjust the middle column so that you still have 108 all the way down. Because for this particular question here, the total project is not going to change. All right, so why don't you take me through the next step?
So then you would do, to find the time for 6 machines, you would do 108 divided by 6. And that's 18.
That's 18.
So then how many fewer hours does it take all 6? You would do 27 minus 18.
Exactly. So the last step is straightforward, right? So your answer is going to be 9. Now, a couple things to think about here. Sometimes, if they want to make this a little bit more difficult, they might do things like, percent, right? So essentially here, if we're going from 4 to 6, you're going up 50%, right?
Right.
You know, so 4 times 1.5 is going to be 6, right? Just like 27 divided by 1.5 is going to be 18, right? So you want to kind of, again, think of the reciprocal relationship between those quantities. That doesn't come into play here, but it could. So you want to be aware that, you know, what you're doing, however much you're scaling something up, you're scaling something down by the same factor, right? So if I'm tripling the number of people or machines or whatever involved in doing something, obviously it's going to take 1/3 the time to do the entire project. All right. So you want to just kind of keep in mind how all these things are, you know, are arranged, how they're all sorted out. Okay. Any questions regarding these particular types of problems before we do you know, one quick rate time distance one?
No.
All right. So you're getting more comfortable with these? Yes,
I do feel better about these.
All
and
right.
it's nice to see it again, because then I'm, you know, I'm affirmed that I'm picking it up.
Okay, all right. So it's not pure repetition then. Which,
no, it's not.
Okay, I'm glad. I know there's a lot of overlap here, and there's going to be a little bit more right now. So, okay, now moving on to the next type of rate problem, which is going to be rate time distance. Okay, problem type 3. Even though conceptually these things are kind of the same, the approach is often different in terms of kind of what they're trying to do. All right. So yes, it's true. It's like, you know, I mean, if you've got something, you know, I mean, you could be dealing with combined rates to get to a, you know, to get to a certain place or something like that. But these are set up a little bit differently. And usually what you want to do is assume that there's probably going to be at least 2 different say situations. All right. So whereas the simplest situation would, you know, would be something like, you know, Michelle is going from Philly to, I don't know, Kansas City, right? She hops on a bus, goes, say, I don't know, 60 miles per hour on average. I have no idea what the distance is, but let's say it's 1,200 miles, right? If the distance is more 1,200, let's say it's like 2,200 miles is okay. This kind of thing is simple, right? This is a simple kind of 3 variable rate time distance, right? You know, you figure it out. It's like, well, okay, our rate is 60, right? Times time, whatever that is going to be 2,200. Simple, you know, pre-algebra, algebra 1 problem. All right. Which is why occasionally you might get that on a GRE type of question, like, you know, not in the if you're not doing all that well, if you're, you know, if you're hitting some of the like an easier stretch, then you might get a question like this. Usually it's going to be more complicated. How are they going to make it more complicated? There's going to be more people. All right. So instead of just having a rate times distance, you might have rate times distance for a couple of different people. Actually, let's do it this way. So actually, you know, we do. Oops. Not sure if there's an undo here. Oh well. I can try. Let's see. Redo. Oh, there it is. Good. Okay. So what they'll do to make it more complicated, they'll have a rate time distance in one situation for, like, you know, person A, but there will be a rate times distance for somebody else. And then all of a sudden we have, you know, dramatically multiplied the number of variables from 3 to 6, which is a lot trickier to solve. All right. So for these kinds of things, it can be useful to think about them on a line. You can set up a table, you can set up a line, but you basically want to visualize what is going on. All right. So there's going to be a couple of different approaches. One might be somebody leaves from a certain point, someone else leaves from a different point, and they meet. All right. So point A, point B. And what you want to look for is ways of reducing the number of variables whenever possible. So the easiest way is when they're going to give you a simple quantity, right? So for example, it's like if they tell you that, Michelle is going 60 miles an hour, great. You've got a 60 to work with. You don't have to work with an R anymore, right? Okay, so that's fine. So then we've gone down from say 6 to 5 variables, right? But then you also want to be on the lookout for clues, right? So for example, if they meet, let's see, okay, let's do it this way. If they meet halfway, then distance 1 equals distance 2, right?
Mm-hmm.
Definition of halfway. All right, so all of a sudden, instead of having 2 distance variables, we've only got 1. All right. If they meet at the same time, well, I say if they meet after leaving at the same time, then time is the same. Then T1 equals T2. All right. If you have a total distance, something like maybe your total distance, say, I don't know, like what I said before, 2,200 miles. All right. And then one person goes, some distance D. How would you express the other distance? What would this be?
Oh, 2,200 minus D.
Yeah, 2,200 minus D. So again, even though we don't have an actual value here, at least we have a way of reducing it from 2 to 1 variable, because D is still D. All right.
Mm-hmm.
Then something that tends to throw people off all the time, I think we talked about this a little bit the last session, is when you have people leaving at different times. All right, because it involves a little bit of thinking backwards.
Mm-hmm.
So if people leave at different times, think about who is going to be faster. And subtract, right, time from that person. All right, so what do I actually mean by that? Well, okay, so for example, if I leave 1 hour later than you to arrive at the same point, I'm faster, right?
Mm-hmm.
Because we're getting to the same point, we're arriving at the same time. But it's like you left at 10 in the morning, and I left at, at 11, and we arrived at noon. So it only took me 1 hour to get there, which means that my time would be T minus 1 hour. All right. It's easy to think about this backwards. So you want to just whenever you kind of, encounter something like this, take a step back and figure out who is going faster. And if you're going faster, it means you're going to take less time.
Right.
Sounds intuitive when you kind of write it out, but when you're in the middle of a problem, make sure you don't have it backwards. All right. Okay, so let's go in again. Let's see. Let's take another look at the first one we looked at last session. Okay. Oh, then the other thing to be aware of, make sure that the units are standard. All right. If you're dealing with hours and minutes, you might be able to work with either one, but do whichever one is easier. All right.
Mm-hmm.
So I know you've seen this before, but have another look at this this question here.
Sure.
Okay, and again, what you want to do, let the question be your guide and look for clues, right? These are all in minutes.
Mm-hmm.
That's potentially important, right? This is not, this is an hour, right? Okay,
Right.
of course, we know that's 60 minutes, but just, kind of keep in mind what you might want to work with. Okay, this is MPH, which is miles per hour, all right? So at some point, there's going to be a conversion. Question is when you're going to do that, And I would say use whichever units are easier to work with. All right. So, and doing unit conversions, work with whichever is easiest. All right. So we've got 25 miles per hour and we've got 60 minutes. So it's up to you. What would you rather work with?
I think minutes, since a few of the answers are in less than 1 hour.
Okay, now keep in mind though.
Hours.
Okay, so what I would say though, it's true that there's going to be a conversion there, but if you're dealing with minutes, you're going to need to figure out what's going on with that 25, right? Because 25 miles per hour is going to be what in terms of minutes?
Sure. Okay.
Right.
And yes, hours.
Yeah. So right. So what would 25? Yeah. What would 25 miles per hour be in terms of minutes?
Well, it'd be 25 times 60. Or no, divided by 60.
Divided by 60, right? Yeah. So you're going to end up with a 25 over 60 here. You sure you want to do that?
No.
Right, exactly. So be careful. So what I would say, another thing too, despite the, I mean, aside from the fact that it's a fraction, it's also a large number, well, comparatively, right? I would rather work with a number like 1 than a number like 60.
Sure.
All right. So while, while you can do it this way, I would say try to, we could work through this way if you like, but it's like, I would say, in general, try to keep it as straightforward as possible. And actually, for the purposes of the class here, I'm gonna shift back to the 1 hour.
Yeah, perfect.
All right. Okay, but all right. So we've got a unit conversion. Now let's actually draw this thing out. What do we know? We've got Samantha's over here. We've got Fred's over here. All right. We know it's 80 miles. Okay, great. We have a rate. She's going 25. And he's going 35. Okay. What else do we know? They're going opposite directions. Okay. What does this mean by the time he passes Samantha? What's the importance of that passing line right there?
It's where they're meeting along that 80-mile.
Exactly. It's a meeting point.
Track. Yeah.
Right. So they're going to phrase that in different ways, but the idea is at some point they're going to be at the same place at the same time. And because they're at the same place at the same time, if they had left at the same time, we'd have t equals t, right? Time equals time. Problem is because we've got an hour shift, we can't quite do that. Okay. Yeah. All right. So we also know our equations. We're solving for Fred's time, right? So let's give Fred the t. 35t equals distance, right? Equals Fred's portion of the distance. All right. Okay. And Samantha, what is Samantha's time going to be?
T plus 1, because she has an extra hour.
Right. She left earlier. It's taking her longer. She's slower. It's taking her more time. More corresponds to plus. Okay. So now we basically have, remember, distance can be expressed as rate times time. So we simply have this part of the distance plus that part of the distance is going to be our total distance, which is 80. Right? So now we have an equation. 25 times t plus 1 plus 35t equals 80. If you wanted to do something like set up a table, you can do it this way. Get your rate times time equals distance. All right, so we've got okay, got a 25 for Samantha, right? We've got a 35 for Fred. We need, now remember, our t, again, this is exactly the same thing, just shifted over. Fred is going to be our regular t with no modification, right? Our total distance is going to be down here, which is going to be 80. Okay. So because as you figured out before, so our Samantha is going to be t plus 1 is going to be her time, right? So the distance for each one, there's going to be 25 times t plus 1. There's going to be 25t. Add them up, and it's going to be 80.
Mm-hmm.
All right. So whether you do it kind of with this picture here linearly, or you do it with a table, it doesn't matter. Same thing. All right. Now you simply go and do the math, right? So now it's going to be, well, okay, 25t plus 25 plus 35t equals 80, right?
Mm-hmm.
If I'm doing my math right, I can't read. All right. So then 60t will equal 55. Our t then equals 55 out of 60. Now, because we figured out already at the beginning, because we were reading carefully that we're solving for time, we're solving for Fred's time, there's not really going to be any additional work that we need to do. 55 out of 60 in terms of hours, that would be 55 minutes.
Right.
All right. Okay. All right, so that's going to wrap things up for the class itself. Hope you've all learned something. I'm going to stick around for probably usually about 10-15 minutes. So yeah, happy to answer questions or yeah. Let me switch back to the thing here. I'll keep the recording going for another couple of minutes. Okay, so yeah, I know there's a lot of repetition here, but yeah. Where do you feel that you're? I mean, so it sounds like you feel like you're progressing pretty well on these types of problems. Any areas where you're still finding you're getting a bit stuck?
Right. Let me go back to the ones I did yesterday.
Mm-hmm.
There actually was a moving walkway one that I got wrong. It was like an airport, like moving walkway, which is something you mentioned earlier in the call. And I think that I fell into the trap that, I mean, do you want to look at it, or how to?
Let's see. Yeah, why don't I let's see. I might kill the recording here. Yeah, hold on 1 second.
Sure.
Yeah, why don't you send it my way?
Yeah, sure. So it's on the GMAT Club, and it starts with Barry walks. If you want to just, or I'll just find it. Hold on.
Okay, so we've got all right, so here, this is a slightly different type of question, but it's still the same kind of thing. Essentially what these kinds of questions are like, question for the class here, is if you've got, think about an airplane, all right? And, let's see, can I draw an airplane? No.
It also feels
I can't draw
similar
that
to the river ones.
Actually, yeah, you're right. Yeah, I can draw a boat on a river. It's easier to draw than a
and then an airplane, yeah.
Plane with it. All right. Okay. So if the boat is moving at some, at some speed, all right, you could have wind, right? If the wind is blowing that way, the total speed is actually going to be, the speed plus the speed of the wind, right? Whereas if the boat is going into the wind, going that way, then the speed would actually be speed minus the wind speed.
Right.
All right. So to figure out, so what's going on here, to find, usually these type of questions are in some way, shape, or form asking you what would be the potential speed of the boat by itself, right?
Without the wind.
And essentially what you're going to have are simultaneous equations, two equations, two variables, right? So what have we got here? Let's, one second. I'll make this bigger so you can see. All right. So
yeah, this is how, yeah.
Okay. So So we've got Barry's speed, some speed, whatever that is. And then we've got a speed of a moving walkway. All right. This is speeding Barry up, right? Anytime you go to an airport, you can figure this out, right? So you're going faster than everybody else. All right. Okay. And how long, equals total distance, like, well, okay, 30 meter walkway in 30 seconds. That's just gonna be 30 over 30, right? Equals 1, right?
Right.
Okay. Because again, it's like here we've got our distance per time, right? It's gonna give you your rate. So your rate is 1. Okay, that is going in one direction. Okay, now if it's going against the walkway, right? What happens then?
It's 30 over 120.
Right, it's going against him, right? 30 over 120 equals 1/4. Right? Now you've simply got simultaneous equations here.
Right. That's what I didn't realize, was that I needed to combine the equations essentially.
Yeah, exactly. Are you comfortable with that kind of process?
Yes.
Okay. Yeah. So yeah, the
It would just be 2b
right,
is equal to 1 plus 1/4.
Yeah. Yeah. So 2b equals 5 over 4. Right. B equals whatever. B equals 5 over 8.
Yeah.
Right.
And then I guess the 5 over 8.
And then you got that 30 there, right?
The third. Oh, yeah. Right. Yeah.
See? Yeah, because saying how many seconds, right? So they're asking you for time, right? So time is going to be what? Time is distance over rate, which is why you're going to divide your 30 divided by 5/8. Right?
Right.
How many seconds? Okay. So it seems like you got the concept okay. So you got stuck in the algebra here.
Well, yeah, I did. I got the individual rates, and then I didn't really know what to do with them to get the without the wind rate. I didn't know that I needed to combine the equations together.
Okay, yeah, I got you. Yeah. So right. So there's really kind of 3 quantities you're thinking about, right? There's kind of your base rate, there's your faster rate, and then the slower rate. And essentially, for these kinds of problems, you're generally going to be asked for the base rate. You may not be. I mean, there may be some modification, but that's generally what's going on.
Okay,
right.
Got it. And that's different from the river ones, because the river ones are often asking for either a time or a distance traveled, or like but it still wants you to incorporate this.
Yeah, I mean, it's still the same concept.
You just need to do the plus the wind or minus the wind.
And because like the only thing, right? Yeah, because like for example, if this were rephrased as okay, well, okay, how fast is Barry moving? Okay, I guess Barry's standing still, right? Whereas if you're dealing with one of the river ones, there's probably going to be some inherent speed to the boat anyway, but that doesn't matter. It's still the same. Still the same concept. All right.
I guess what I'm saying is the river ones are asking you for, like, they're giving you the fact that the wind is X speed, and then it's maybe asking for the seconds. Or
okay, yeah, yeah.
Like it's asking for different variables where combining the 2 equations isn't really like the strategy, right?
Yeah, I see what you're saying. Right. So if this said like the walkway goes 2 meters per second or whatever.
Right.
Yeah, exactly. Yeah.
A different way.
Right. Yeah. So these things, I mean, they're always, again, there's 6 variables, anywhere between 3 and 6 variables that could be asked, right? So you never quite know which ones are going to give you and which ones they aren't, right?
Yeah.
But yeah, essentially, I mean, the concept is always this is a little bit of a different type of problem, these and the river ones and things like that, in that you have your action working towards and actions working against. So it's a little bit different. But yeah, it seems like you handled most of this pretty well, except for the
the combo. Yeah, I didn't know how to do that.
Yeah.
Or I know how to do it. I didn't know that's what I was supposed to do.
Yeah, gotcha.
Okay.
Okay.
Thank you for the
So
extra
I'm
help
gonna,
there.
sure, absolutely. I'm gonna cut the recording here. And